Okay, so as a यो लाइसेन्स बाट प्रोबेबली फर्स्ट अब सेमिनार क्लास होला हैन
फर्स्ट
ल त्यही भएर मैले यसो ब्रिफली बताइदिहालेँ ओके welcome all of you to this seminar talk, particularly for this third semester student. And in addition to third semester student, there are fourth semester my thesis student, as well as probably I have some collaborators whom I invited as well. So hopefully they will appear soon. So today what I'm trying to do is I'm trying to discuss what recently we have done. I mean the research work that has been done and was published in a very good scientific journal, that is Nature Materials. Okay, so this is the title of my presentation. Before actually going on to the depth of what is the meaning of Dirac fermions and flat bands in this Kagome iron tin, if you see the title, you need to know a number of things. Let's suppose, what are these fermions? I suppose you can see the arrow. Unfortunately, I forgot to mark it with a different color. I'm using Windows at the moment. That's why it is not marked in this form. But anyway, so we need to know different parameters based on which we will understand what this topic means. So you need to know what are fermions, which I think most of us already are familiar with. You need to know after fermions what are Dirac fermions, why fermions are of different category. Some are called as wild fermions, some are called as fermions only, and some are called Dirac fermions, as you can see here. What is the reason behind that? We need to understand. And then in the meantime, here on the title, what I have written is the flat bands. Okay, what do we mean by flat bands? That too in the electronic band structure. We need to understand this thing. And then the wording that I have given, or we have given, is ideal. Ideal is well known to every one of us, I think. So it is peculiar or particular. That's why we named it as ideal. And then there is another before I start now to flow with my presentation, I would like to thank this Alexander von Humboldt Foundation, who supported me actually for this and other research while I was in Germany. And this is the institution where I worked before I come to our institution, wherein 40% of this work is completed from this Central Department of Physics, and the remaining was from this 60% was from this IFWS. For your information. Okay, this is the outline of my talk. So in this outline, what I try to discuss is about the basic concepts of the Dirac fermions and the flat bands. This is the figure that I have shown, which will distinguish how a fermion can become a Dirac fermion and then a wild fermions. So this figure will tell you. And then I will discuss also about the semi-metals. We have been talking about a number of systems, some of the systems with a band gap, some of the system with a larger band gap, let's say insulator, and some of the system with purely metallic. But we will be talking here about the semi-metals. Means that they look at 0 Kelvin, they look almost like an semiconductor, but at certain temperature level, they, because of the transfer of some of the electrons from valence to the conduction, they show metallic property. That's why they lie in between, and we call it as a semi-metal. So these are of two kinds which are recently of high research. Where is the mouse? Okay. So this is the section. Can you see, guys? Sir, your arrow देखिएको छ sir? White arrow. Okay, hopefully you see. And then I will also discuss about the crystal structure, because I mentioned about this kagome. So the structure of this iron tin looks something like this if we look from the plane. Hey, crystal structure la हामीहरुले हेर्दाखेरि 3 dimensional मा कस्तो हुन्छ, x, y र z direction हुन्छ. So only plane यानी AB plane बाट यसरी हेर्यौं भने चाहिँ यो it looks something like this. Okay, it looks something like this. And I will discuss about this in more detail. And then I will focus mainly on what our results we have found in this particular material, and then try to summarize it. Okay, so the strategy particularly we have applied for our calculation means the density. My part is that I perform the theoretical calculation, which we call basically as density functional theory calculation. And here we try to address the electronic, magnetic, and surface property, as well as the magnetic anisotropic properties. That's why what you see here is here anisotropy is there. And I will also further discuss about what our collaborators have done experimentally. For the DFT part, we need some sort of software. You can do a programming, of course, by writing a script, by writing a programming. But here what I have done is I have used our own institutional generated software. Our institutional means the institution IFW Dresden, Germany, where I have been working. So we have our own software that is the full potential local orbital code. So this works both in scalar relativistic as well as full relativistic form. So when I say full relativistic, it means that we need to include spin orbit coupling in addition to the normal spin polarized calculation. And we further need the functionals, and we have used this GGA functional. Using the enhanced basis set means we try to take into account a large number of orbitals which can contribute to the Fermi level. Okay, then we need some sort of mapping in order that we can find out the real surface property as well as wild properties. That's why one-year band mapping needs to be done, which I have done. Okay, this is the computational package that I have been saying. This computational package, which is also called as FPLO, is a licensed package. It has a number of features, which is shown here. As you can see, it uses Python script based on DFT, designed for high accuracy, efficiency, and stability of the numerics. And it is suitable for up to 300 atoms on a single CPU machine. This is its highest priority. This is the reason that this software becomes highly prioritized, and the memory that it uses is really compared to other softwares is really less. Okay, so let us now try to enter and try to understand what electrons in solid particularly means. I know that almost all of us has a very clear and good understanding of this slide. Even then, I will try to make something very clear. And where does that semi-metal lies? How do we see that in the energy dispersion picture? Or that energy dispersion picture which we called is nothing but it is the band structure calculations. So let's have a look on this this section, left section. So what you see here is sub number A is considered as a metal. This is based on the dispersion of the bands starting from the Fermi level. Again, let me clarify just one first, this one. Forget about this. So let us say that this is my figure. In this figure, I have a dotted line here. So this dotted line represents the Fermi level. And from our BSc teaching, what we understand is they are the level where the maximum number of electrons can be occupied. That separates actually the Fermi level actually separates the occupied bands, which we called it as a valence, and the unoccupied bands, which we called it as a conduction. So along the y-axis, you measure the energy, right? And along the x-axis, let's say along this direction, you measure the dispersion of those bands. So in between, you have a Fermi level, and if the bands of the below the Fermi levels are crossing, you see here, this is the blue, which implies that they are fully occupied, right? And the bands are moving on to the Fermi level. So they are crossing the Fermi level. This dictates that it is a metal. Now let us go to the second sub. This is an insulator. How do we differentiate this, that it is an insulator? Basing on the gap formed between this conduction band and this valence band. Valence band was an occupied band. So we call, because they are separated with a gap, they are an insulator. And here, just for you to understand, we have mentioned it here as a gap of the order of 4 electron volt. And if I have to compare or differentiate between the insulator and a semiconductor, how do we differentiate is by looking at the band gap. See, you need to, here you need to, how do you distinguish? Some people, they may say that, okay, the size of the band gap is just 1 electron volt or 1.1 electron volt. It should be a semiconductor. It should not be an insulator. That is not true. It is true only when you are considering that in terms of 0 Kelvin. And that too, only for an elemental case, it is said. If it is the case of what we call the compound, then usually, if the band gap size is of the order of 0.1 or above, the convention they use in general case is an insulator, despite the fact that the gap size is very, very small. So don't get confused if the gap size is too large or too small. You just need to recall or remember that there is a gap in between them. So for now, if you try to understand between insulator and semiconductor, for 0K, to the elements, to those elements, then you can say this statement, you can use this statement. But that is not true for the compound cases at 0K. If it is higher, that will completely change. But they are true only for the elemental case. I'm focusing more and more to this particular thing. Okay, after that, let us have a look on this one. What do we see? Here we see that the upper band, which I called it as a conduction, and the lower occupied, which I called it as a valence, they are crossing with each other or touching each other at the Fermi level. So this Fermi level, this is just for your understanding we have put here, okay? So this Fermi level, because of the doping effect, this Fermi level may shift also. So this Fermi level may go slightly below the in the valence region and above in the conduction region. But the important point that you need to remember is that they are touching each other and there is no gap in between them. But at the Fermi level, there is a very finite density of state. If that is the case, you call that as a semi-metal. Now, once I have this one, let us go on to the right-hand side of our figure. So in this right-hand side, what do you see? You see that this is an insulator here. This is also an insulator here. In between, what you see is a semi-metal. So this semi-metal is nothing but it is this one. But what is the difference in insulator you have seen? One is called as a trivial insulator and the another one is a topological insulator. So this is quite interesting. Interesting in the sense that if I have to define the insulator, so insulator means it is the material with a sizable band gap, whether it is at the bulk or at the surface. है यो ख्याल गर्ने कुरा चाहिँ सर्फेसमा पनि र बल्कमा पनि यसले के देखाउनु पर्यो भन्दा साइजेबल ब्यान्ड ग्याप देखाउनु पर्यो। त्यो भयो भने त्यसलाई हामीहरूले ट्रिभियल इन्सुलेटर भनेर भन्छौँ। तर टोपोलोजिकल इन्सुलेटर भयो भने पनि हामीले कसरी छुट्याउँछौँ त भन्दाखेरि बल्कमा त्यसको ब्यान्ड ग्याप छ, तर सर्फेसमा तिमीले जब त्यसलाई काट्छौ, काट्दाखेरिको त्यसको सर्फेसमा तिमीले ब्यान्ड ग्याप मेजर गर्यौ भने चाहिँ त्यहाँ तिमीले मेटालिक फेस देख्छौ अथवा सेमी मेटालिक फेस देख्छौ। त्यो हुँदा बित्तिकै तिमीले त्यसलाई के एज्युम त्यो टाइप अफ मेटेरियल भनेको के त भन्दा एक साइडमा एउटा प्रोपर्टी छ, अर्को साइडमा अर्को प्रोपर्टी भएको हुनाले त्यसलाई टोपोलोजिकल इन्सुलेटर और नन ट्रिभियल इन्सुलेटर भनेर भनिन्छ। भनेपछि अब यो एउटा फेजबाट अर्को एउटा फेजमा जाँदाखेरि त के हुने भयो भन्दा तिमी बल्कबाट सर्फेसमा जाँदाखेरि त्यसले के गर्छ, बाटो ट्रेस गर्दै जाँदाखेरि आखिर त्यसलाई चाहिँ गो थ्रु गरेर कहाँ जानु पर्यो भन्दा कन्डक्सन ब्यान्ड फर इन्स्टेन्स यहाँ हेर तिमीले यहाँ तल्लो ब्यान्ड इन्भर्जन हेर, यहाँ हेर्दाखेरि के देख्यौ प्लस भनेको अक्युपाइड ब्यान्ड हो, माइनस भनेको अनअक्युपाइड ब्यान्ड हो। फर्मी लेभलले छुट्याएको छ यिनीहरूलाई। जब तिमीले सर्फेसतिर जाँदै गर्छौ जाँदाखेरि के भइदियो भन्दा यो चाहिँ स्लाइटली डिराकोन लाइक स्ट्रक्चर भयो। फर्मी लेभललाई क्रस गर्दाखेरि भ्यालेन्स ब्यान्डबाट पनि यो ब्यान्ड अक्युपाइड ब्यान्ड आएर एक अर्कामा क्रसिङ गर्यो। अनि यहाँ क्रसिङ गर्दा बित्तिकै यो फिचर चाहिँ के भयो भर्खरै हामीले डिस्कस गरेको यो एउटा फिचर। देन अब यो एउटा फिचर भइसकेपछि यहाँबाट तिम्रो के भइदियो भन्दाखेरि मेटालिक त देखाइसक्यो। अब टोपोलोजीमा कसरी यो चाहिँ नन ट्रिभियल भयो भन्ने कुरा चाहिँ के भन्दा यो जुन तल्लो ब्यान्ड थियो नि यो माइस्फेरिक ओके, यो जुन ब्यान्ड छ अब यो ब्लू ब्यान्ड चाहिँ यता हेरेर त के भइदियो भन्दा यसको पार्ट अफ द ब्यान्ड्स यो इन्भर्ट भएर कता गयो कन्डक्सन रिजनमा गयो। अनि कन्डक्सनको जुन रातो ब्यान्ड थियो त्यो त ट्रान्सफर भएर कता गयो इन्भर्ट भएर भ्यालेन्समा। यानी यहाँ चाहिँ ब्यान्ड के भइदियो त भन्दाखेरि इन्भर्ट भयो, एउटा डाइरेक्सनको पार्शियल ब्यान्ड अर्को डाइरेक्सन अर्को रिजनमा गयो एन्ड भाइस वर्सा। सो द्याट्स वाइ अनि मेन्टेन चाहिँ के गर्यो यसले भन्दाखेरि ग्याप चाहिँ मेन्टेन गर्यो। सो दिस इज वाट इज कल्ड एज द टोपोलोजिकल इन्सुलेटर। अब यहाँ तिमीहरूले थाहा बुझ्ने कुरा के भन्दा यो चाहिँ बल्क र बल्कको बिचकै कुरा गरिरहेछ। यो हामीहरूले बल्कमा पहिला हेर्न पर्यो भने पर कसरी बुझ्ने त यसलाई भन्दाखेरि हामीहरूले यसमा रिलेटिभिस्टिक क्याल्कुलेसन गर्नुपर्ने हुन्छ। हेर यहाँ अगाडिपट्टि मैले यो ट्रिभियल इन्सुलेटर भनेर जुन छुट्याएँ यो स्पिन अर्बिट कप्लिङ लगाएपछि मात्रै मलाई त्यो मेटेरियल चाहिँ मेटालिक हो कि नन सरी ट्रिभियल compound that we have studied, which was recently published in physical review research. This is a rapid communication है। यसबाट मैले देखाउन खोजेको मात्र के हो त भन्दाखेरि यहाँ मैले दुई प्रकारको स्ट्रक्चर देखाउन खोजे हो। एउटा चाहिँ एलिमेन्ट हो, हेर यो चाहिँ कोबाल्ट को मात्रै केस हामीहरूले स्टडी गरेका हौं है, यही सेम पेपरमा छ। अनि अर्को चाहिँ कोबाल्टको कम्पाउन्डको कुरा गरिरहेका छौं। यो हो CO3, यहाँ हेर त CO3SN2S2 को यो क्रिस्टल हो, ब्रिलाउन जोन हो सरी, त्यसको क्रिस्टल स्ट्रक्चर यो हो। अनि यसको क्रिस्टल स्ट्रक्चरमा तिमीले हेर्यौ भने पर के देख्छौ कोबाल्ट छ, सल्फर छ, टिन छ। अब यो क्रिस्टल स्ट्रक्चर कस्तो खालको मेन्टेन गरेको भन्ने कुरा अगा पछि आएर मैले भन्ने भएको हुनाले यसमा मैले खासै फोकस गरिन। मैले यहाँ देखाउन खोजेको मात्रै के हो त भन्दाखेरि डिपेन्डिङ अन कम्पाउन्ड यानी सरी एलिमेन्टको कम्पोजिसनको आधारमा क्रिस्टल स्ट्रक्चर डिफरेन्ट सिमेट्रीमा गएर बस्ने गर्छ। त्यो तिमीहरूलाई वेल एवेयर छ होला। कोही चाहिँ क्युबिक स्ट्रक्चर हुन्छ, कोही टेट्रागोनल हुन्छ, कोही गएर हेक्सागोनल हुन्छ। हेक्सागोनलमा पनि अब रोम्बोहेड्रल टाइपको हुन्छ कि कस्तो हुन्छ त्यो सबै सिमेट्रीमा तिमीहरूले पढिसक्यो होला क्रिस्टल सिमेट्रीमा। एनीवे, सो हियर व्हाट आई वान्ट टु शो यु इज सी हियर यो यतापट्टिको जुन कोबाल्ट छ प्योर कोबाल्टमा मात्रै के भइरहेको छ भन्दाखेरि यसको हेक्सागोनल स्ट्रक्चर छ जुन मैले यहाँ देखाएँ। अनि यो चाहिँ के छ, यो चाहिँ रोम्बोहेड्रल टाइप स्ट्रक्चर छ है। अब ब्रिलाउन जोन त्यसैले गर्दाखेरि यिनीहरू दुईटाको फरक पर्यो। अब यो फरक पर्दा बित्तिकै अब यिनीहरूको जुन ब्यान्ड डिस्पर्सन हुन्छ, तिमीहरूले त ब्यान्ड डिस्पर्सन अगाडिपट्टि के देखेका थियौ, यस्तो भनेर मात्रै देखेका थियौ, px यता py यता अनि त्यहाँबाट यतापट्टि चाहिँ के भन्दाखेरि एनर्जी भनेर देखाएको। यो px py भनेको यो के हो, मोमेन्टम स्पेस हो। त्यो मोमेन्टम स्पेस चाहिँ हामीहरूले ब्यान्ड स्ट्रक्चर क्याल्कुलेट गर्दाखेरि यो ब्रिलाउन जोनलाई हेरेर यसको ब्रिलाउन जोनको रेस्पेक्टमा हामीहरूले प्लट गर्ने हो। So this you have to be aware of. So what is happening, because the Brillouin zone is different, is you can see here the location or the direction along which I plot the band dispersion are different. अनि यसमा इम्पोर्टेन्ट पोइन्ट्स भनेको यो वाइल्ड पोइन्ट्सको बारेमा हो जुन म अगाडि गएर कुरा गर्छु। जस्ट इन्फर्मेसनको लागि यहाँ हेर, WP भनेको वाइल्ड पोइन्ट्स हो, हामीले कोबाल्टमा पनि भेटाएका छौँ। अनि त्यहाँबाट यो कोबाल्ट 3 सल्फर यानी CO3SN2S2 जसलाई स्यान्डाइड कम्पाउन्ड भनेर भनिन्छ, यसमा पनि हामीहरूले भेटाएका छौँ। पोजिसन फरक फरक छ है। सो क्रिस्टलको डिपेन्डिङ अन द टाइप अफ क्रिस्टल द band structure in its momentum space are different. Okay, now let us come to this very interesting topic. How do we distinguish the Dirac fermions from the normal fermions? So basing on this particular Hamiltonian, I think we are very much aware. So what is happening in the Schrodinger fermions, the normal Schrodinger fermions has a Hamiltonian H, which is depending on the momentum P, right? So this is the expression for the normal Schrodinger fermions. Now, so this is the electron that is rotating about, which is giving rise to the electronic properties. Now, the another thing is the ultra-relativistic Dirac particles. Now, what is happening here? In this case, you are applying what? The relativistic term, yani spin orbit. किन भन्दाखेरि हरेक इलेक्ट्रोन तिमीले ब्याचलर्समा स्टडी गर्दाखेरि के स्टडी पनि गरेका, स्केलर भन्ने एउटा स्टडी गरेका छौँ जुनमा रिलेटिभिस्टिक टर्म आएको छैन, अनि अर्कोमा चाहिँ रिलेटिभिस्टिक टर्म आएको छ जसमा चाहिँ के हुन्छ, इलेक्ट्रोन हेज देयर आउन स्पिन बिकज अफ व्हिच दे आर रोटेटिङ अबाउट देयर एक्सिस, राइट? So and they give rise to this relativistic phenomena wherein the velocity of light is involved along with the spin. You see here your sigma denotes that spin term. Hey, and therefore what you see the difference between these two, यसमा के डिफरेन्स देख्यौ तिमीले भन्दाखेरि यो चाहिँ स्पिनको डिफरेन्स देख्यौ, अनि अर्को डिफरेन्स सँगसँगै के देख्यौ भन्दाखेरि यो ब्यान्ड डिस्पर्सनमा हामीहरूले यसमा अक्युपाइड स्टेट जुन तल्लो छ यो ब्लू र अनअक्युपाइड स्टेट यो, यानी यसले एउटा डिनोट के गर्छ भन्दाखेरि होल र इलेक्ट्रोनको कन्सेप्ट यहाँ जेनेरेट गरेको छ, which is based on ultra relativistic Dirac particles. So they are linearly, there is a linear crossing between the bands, between the two bands. Now, if I go to this another form, what we call it as a Dirac fermion. अब यो Dirac fermion को केसमा यसलाई चाहिँ स्टेटमेन्ट दिँदाखेरि के भनिएको छ, massless. Note, it is not actually massless. Okay, only the thing here is that there are the electrons whose spin moments, their polarization are completely opposite to each other. I mean, up spin and down spin, they are cancelling each other, and then the overall features that it looks like is a massless light. So this is differentiated with what? With the red and the green color that you can see here. So here, what you have found is instead of this, what we call velocity C, we have the velocity. This is the motion of this particular electron with the fermionic velocity that we call it as a Vf. So the expression is differentiating, and the Hamiltonian for this one can be seen here. Okay. Okay. Now I will come. Maybe after this one I can go a bit faster, thinking that you understand. So, if you are aware, I think most of us are aware that graphene is that particular material which has been found by these two gentlemen, Gaim and Novoselov, and because of their work in 2004, which was reported here in Science in volume 306, they found this graphene to act as a Dirac fermions, two-dimensional Dirac fermions. So sometimes back, what we were discussing about this feature, massless Dirac fermions. So they are able to observe these features where in graphene, which is nothing but graphene is the overlay of a number of carbon atoms into two-dimensional space wherein they form a hexagonal-like structure. See here. So all these are the carbon atoms which are arranged alternatively. Actually, they have two sides. One of the sides, if I consider it as A, another side is A prime. So the location or the position of those two are inequivalent, and as a result, they are able to form the hexagonal face that you have seen it here. अब यो फिचर तिमीहरुले कार्बनमा बनाउन खोजेका छौ भने पनि हेक्सागोनल स्ट्रक्चर लिनु पर्यो, 3 डाइमेन्सनबाट 2 डाइमेन्सनल बनाउनु पर्यो, अनि एक्स वाई प्लेनमा तिमीहरुले के गर्न सक्छौ भन्दाखेरि त्यो एक्सिसलाई चाहिँ इलोंगेट गरेर प्लेनमा हेर्यो भने पर तिमीहरुले देख्छौ यस्तै खालको फिचर देख्छौ. ओके, अनि यो फिचर यो यस्तो खालको कम्पाउन्डमा के देखियो त भन्दाखेरि ब्यान्ड क्रसिङ देखियो यहाँ यसरी यो रिजनमा at a high symmetry points. यो 0 ले इन्डिकेट गरेको के हो त भन्दाखेरि हाई सिमेट्री पोइन्ट्स, दिस इज गामा पोइन्ट है. अगाडि हामीहरु जस्ट म फेरि ब्याक गए एकैछिनको लागि, यो कोबाल्ट यो जुन छ नि हो, यही कोबाल्टको स्ट्रक्चर हो त्यो ग्राफिनको पनि जुन चाहिँ हेक्सागोनल स्ट्रक्चर छ है. र यो 0 जुन उतापट्टि 0 देखाएको थियो यो पोइन्ट हो है, गामा. और यहाँ चाहिँ हामीहरुले गर्दाखेरि हाम्रो कामको लागि हामीहरुले के गरेनौ भन्दाखेरि हामीहरुले त्यो डाइरेक्ट यसमा प्लेन हेरेनौ गामा एम के गामा भनेर चाहिँ हामीलाई चाहिँ वाइल्ड पोजिसनको लोकेट गर्न मात्रै छ. तर त्यो हेक्सागोनल स्ट्रक्चरमा के हुन्छ त भन्दाखेरि हाम्रो एउटा प्लेन हुन्छ, एक्स वाई प्लेन हुन्छ अनि जी डाइरेक्सन हुन्छ है. त्यो एक्स वाई प्लेन भनेको के भन्दा यो सेन्टरमा गामा छ, यतापट्टिको एउटा साइडमा एम छ है, यतापट्टिको गामा के छ अनि फेरि गामा. सो यो गर्ने भने पर हामीहरुले ओभरऑल 2 डाइमेन्सनल पिक्चर ड्रा गर्न सकिन्छ, जुन चाहिँ यिनीहरुले ड्रा गर्दाखेरि यो खालको फिचर obtain गरे अनि त्यसलाई एक्सपेरिमेन्टल प्रुफ पनि गर्न सके, सफल भयो. र यस्तो खालको मटेरियल्सको के हुन्छ त एप्लिकेसन, के न चाहिँ बढी मान्छेले ध्यान दिएको भन्दाखेरि यस्ताले जीरो इफेक्टिभ मास है, effective mass only. So you need to think about this one. Zero effective mass, which give rise to a very high mobility, and high mobility quantum effects are very, very robust. And then this type of quantum robust, which is shown here linearly, this can retain, your phase retain even up to higher temperature सम्म हुन सक्छ, जुन उनीहरुले क्लेम गरे अनुसार चाहिँ रूम टेम्परेचर सम्म पनि सस्टेन गर्न सक्छ, प्रोवाइडेड दैट अरु एन्भाइरोमेन्टल इफेक्ट भएन भन्ने खालको. सो इन दैट कन्टेक्स्ट डिराक फर्मेन्स आर भेरी भेरी गुड मटेरियल. ल है, मैले यसलाई चाहिँ अब कता जोडे त भन्दै हाम्रो यतापट्टिको आइरन टिनको कम्पाउन्डमा मैले जोडे है. आइरन ट्युनमा हामीहरुले के पत्ता लाग्यौ भन्दाखेरि डिराक फर्माइन्स नै पत्ता लागेका. हामीहरुले अरु बडी काम गर्नुहुँदा आइडियलको बारेमा पछि कुरा गर्न एउटा प्रपर्टी हामीहरुले पत्ता लागेको भनेको चाहिँ डिराक फर्माइन्स पत्ता लाग्यौ. केमा पत्ता लाग्यौ भन्दाखेरि एउटा कम्पाउन्डमा, ग्राफिन जस्तै एउटा आइरन टिन कम्पाउन्डमा पत्ता लाग्यौ. तर त्यसमा के एडिसनली थपिएको छ भन्दा म्याग्नेटिजम थपिएको छ, जुन चाहिँ त्यो ग्राफिनको केसमा छैन. इट इज नन म्याग्नेटिक. ओके, दैट इज हाउ one can separate. Okay, sir, I think 5 more सरले सुन्नु भएको छ भने I think 5 more are there on waiting for your approval to enter to this talk. Okay, let me continue again. So in addition to that, what it has, what property again it has is high electrical current, thermal conductivity and stiffness. In addition, impermeable to gases. So they are even impermeable to gases. That's why they are very, very applicable for the technological application, technological device, sorry. So let us now come to that fermions, how it is mathematically done. See, Dirac fermions as a whole, if I have to say effective nonlinear, but it is a massive particle. यो massive कुन सेन्समा यहाँ भनेको छ त्यो पनि बुझ्ने कोसिस गर्नु है फेरि। अब मैले कम्पेयर उतापट्टिको अरु फर्माइन्सलाई कुरा गरे हैन, मैले डिराक फर्माइन्सलाई एउटा फर्माइन्स भनेर लिएको छु। त्यो फर्माइन्स चाहिँ उतापट्टि जुन मासलेस भनेको थियो यहाँ चाहिँ म्यासिभ पार्टिकलको कन्टेक्स्टमा आएको। कारण के, यसलाई हामीहरूले एउटा रेफरेन्स लिएको जसबाट हामीहरूले दुई प्रकारको इलेक्ट्रोनिक फिचर देखेका छौं। जसरी हेरौं त यतापट्टिको राइट ह्यान्ड साइडलाई